I'm Dan Sachs, and there's my topic. Let's just do it. This is really, the whole thing is focused on a particular use of the keyword friend that I think it's an interesting little corner case. And so what I'm really going to do is show you the technique, but what I think is really interesting is all the little bits and pieces that go into the backstory. The interest is in the details. This is very code intensive. And so I'll just alert you, there are going to be pieces where I'll show you, and your attitude will be, come on, show me something I don't know. But my experience is if I leap ahead on this and all of a sudden dive in the middle, how did you get here? So just let me just sail through it, but don't hesitate to stop and ask me a question of clarification if there's anything that you'd like me. I prefer to be interrupted while I'm talking rather than do all this stuff at the end. So anyway, what's friendship about in C++? It's a keyword. You can put it in a class associated with a function or another class. And what its primary role is to grant access to the class granting the friendship to something that normally wouldn't have that access. And you use it judiciously because you don't want to. Access control is a big deal in C++. You don't want to give it away unnecessarily, but there are clearly times and places that you need to do this. But what I'm going to do is show you a use for the keyword friend that's actually not about granting access. It's about making something else click. And in this example, I hope you'll be able to see that what it does is it actually simplifies the implementation of certain aspects of a class, and it also produces a better interface as a benefit. So what I'm going to use as my example is a class for rational numbers. I think it's a nice, easy to understand example because most of us know how to do fractional arithmetic. We know what the purpose of something like this would be. And what example use cases would look like. Now, in order to keep the examples readable, I've left out certain details, like there is an ample opportunity to use const expr in the code you're about to see. I'm not doing that, just because it adds verbiage and clutter to the slides, but just remember there's uses for it. Also, you could say the same thing about inlining. I will throw the keyword inline in a few places, but not in every opportunity, just, again, to minimize clutter in the code. So here is a first cut at a class for rational numbers. In this particular case, my starting version, it's not a template. It's just a class that implements the numerator and denominator of the rational numbers as signed long integers. And as you might expect, it has a small assortment of constructors that let you do things like make me a rational with a reasonable default value, make me a rational number whose initial value is the same as some integer. So for example, not surprisingly, if you say make me a rational whose value is 3, you get 3 over 1, that sort of thing. And it has the default implementations for the copy constructor and copy assignment because this is a data type that has a shallow implementation. The compiler-generated copy operations work just fine. And it has no move semantics, so we don't have to worry about R-value references on the move operations. And it also is going to have, there's just one teaser there, a plus equals operator. It's one of many arithmetic operations that you would provide for a class like this. But I've drawn your attention to the converting constructor. And now what makes it a converting constructor is, well, there's a little disclaimer here. This is the old definition. It's good enough for our purposes. In C++ 03, you would simply say a converting constructor is any constructor that can be invoked with a single argument. Now, it could actually be a constructor with more than one parameter if the parameters have default values. The key thing is you can call it passing it one thing. And it's not declared with the keyword explicit, because the keyword explicit is there to turn off the property of a converting constructor. And in an arithmetic data type like rational, it turns out the converting constructor is a really powerful tool for providing an interface which makes this arithmetic type behave like the built-in arithmetic types. In particular, you can do things like that. R1 plus equals 42, where you're adding an integer to a rational number. Seems like I have to make sure I don't use the word rational. You know, it seems like a rational thing to do. It seems like a fairly intuitive thing to do. The understanding is, though, that when you write that R1 plus equals 42, the compiler steps in and says, I don't see a function whose signature exactly matches that. But if I apply the converting constructor there, I will get an argument match. So it will on the fly manufacture a temporary object of type rational initialized with the value 42, as if what's shown on the bottom of the slide is really what gets done. It's that we're creating a temporary object and then using it and then throwing it away. That's the as-if model. And compilers are pretty good at optimizing this stuff, but conceptually, that's what's happening. Now, in addition to the assignment operators like plus equals, minus equals, the class ought to have binary operations like just plus, minus, times, and divide, where you could say R1 plus R2, something like that. Now, here's where we run into an interface problem, which is not too hard to solve, but if we want this thing to really look like a built-in type, we should be able to say not only R2 times 2, but 2 times R2. It should be symmetric in that you don't have to have both a rational as the left and right argument. You can use mixed arithmetic just like you can with integers and floating values. And based on what I showed you, this doesn't work. And the reason is that the second one has a non-rational as the left operand of the multiply. And when on the previous slide, notice that these operators are all implemented as members, which have an implied parameter this, which is the left operand of those arithmetic operations. The compiler will not employ those member functions when the arguments are an int and a rational. It won't do a conversion on the left operand. And so this is the conventional reason for implementing these things as non-member functions rather than as members. It's so that the compiler, during overload resolution, will try to do a conversion either on the left operand or on the right operand. If those operations are implemented as members, it will only try the conversion on the right operand. That's sort of like one of the canonical examples for why we would use non-member operators. Now, the implementation is fairly simple and straightforward. It's just return a rational constructed by multiplying the numerators and multiplying the denominators. Implementation is really pretty trivial. But the little twist here is, this is now a non-member function, and it's implemented by referring to private data in the class, and that's an access problem. So what do? Well, one way to do it is to grant friendship. This is what a lot of people think of as a legitimate use for friendship, and it arguably is. And now you can go ahead and implement all of the operators multiply, divide, add, subtract as friend functions like this, and the bodies are all just the straightforward operations that I just showed you. Now, but there's an arguably a better way to do this, which is that one of the properties that you would expect, based on your experience with the built-in types, there is a relationship between the multiply and the multiply equals, between add and add equals. You would hope they would produce the same arithmetic result. And during a code review, that's one of the things that you might want to assure yourself of, that, hey, if I use star equals or star, I'm going to get the same result. It's just delivered to me in a slightly different way, but it's the same numeric result. One of the ways to assure that is, why don't you just implement one in terms of the other? And it turns out to be very natural to do it this way, to simply implement the non-member operator star by calling the star equals to do the math. Okay. The hitch in this particular packaging, though, is notice that the operands of the operator star are both passed by reference to const. We do that. This is an example of using pass by reference to const to mimic the behavior of pass by value. And in this case, the fact that the left operand is by reference to const means that you can't use either the left or the right operand to accumulate the result. If you say x times y, you don't expect to change x and you don't expect to change y. You expect the answer to go somewhere else. So you have to have a local object to hold that result. And then you use the star equals operator there. But in fact, there's a clever way to avoid having to declare that local object, and that is to do it this way. Like that. It just cuts out a lot of code. I use that weird spacing there just so you can see the difference. And the difference is I'm making the left operand passed by value, so it in effect is the local object that accumulates the result. And because it's not declared const, it's just passed by value, you still have the assurance that the actual call doesn't modify the left or the right operand, and I didn't really examine this carefully, but I suspect that modern compilers will do a pretty good job of optimizing both of these into the same thing. But if one is going to win, this one might be more conducive to optimization. And this avoids granting friendship. Now, in this particular case, we have an obvious relationship between the multiply and the multiply equals operator. That it's very natural to want to implement multiply in terms of multiply equals. And that's true for add, subtract, divide. It's not true for every one of the operators. For example, there isn't this relationship between greater than and greater than or equal to. Right? It's not the same natural fit, that one is obviously a member and the other one is not. So in the case of something like a greater than operator, it's not obvious that there's some member that you can call on. You might just be inclined to just make the greater than a non-member and make it a friend, and it accesses the numerator or denominator directly. So in this case, granting friendship might be simpler. Here's the other sort of canonical example for why you use non-member functions instead of member functions, and that is if I want to implement an output operator. Use the shift operator in the conventional way that it's used with the stream operations. Now, in order to be able to output a rational number, again, you need access to the numerator and denominator. You need to be able to display those. And so it seems at first blush that what we want to do is declare the output operator as a member of the rational class. Now, clearly we don't want, you will not be very popular if you go and start editing IO stream to change the stream class to include a rational operator, output operator. That's not the way you go about it. You go about doing it by augmenting the rational class to provide the output operation. So you make it a member. The problem is if it's a member of the class, the rational number is going to be on the left and the stream will be on the right. Because once again, that's where the expected placement of the class object is in a member function is it's on the left. And this doesn't mesh well with all of the other stream operations where the stream is on the left. So how do you fix that? Well, that's another use for a non-member function. Now, in this case, the non-member function is not being used because we want to permit conversions on either the left or the right operand. We just want to control the order in which we declared the arguments to the operator. We want the stream to be on the left. If we make the output operator a member of the rational number class, we're going to wind up with the stream on the right, and we don't have any choice. This gives us a choice. So you make it a non-member, but it still needs access to the numerator and denominator of the rational number. So it looks like it needs friendship. Right? There's the implementation. It needs to be a friend. But a common idiom is to go ahead and declare a member function called put, where the invocation looks like the last line just before the curly brace, where you say, oh, the output stream dot put rational number. It doesn't look very pretty, but it does the job well. And then you implement the output operator as a as I describe it, a paper-thin wrapper around a call on that not so attractive output operator, the put function. And again, you always have to stop and think, is it worth my while to create, in a sense, this member function that I'm not going to ask anybody to use and create it as a public member function just so that I don't have to grant friendship here? That's a call that you have to make. But one way that you can tip the balance in favor of that function is that sometimes you wind up implementing that put function as a member of a class in a hierarchy. You have a base and a derived class, and you put the put function in the base class and make it a virtual function so that you can override it in the derived classes. It then turns out that using this idiom actually gives the output operator polymorphic behavior if it's implementing in terms of a polymorphic put function. Oh, yes, that probably is. Yes, that is a typo. Thank you for catching that. Let's just fix that, just so that everybody sees clearly what it is. It's very nice to know. In fact, that's a reason to plant typos. It's the way you can find out if people are actually listening to you and paying attention to what you're saying. Yes, that's right. So I did that on purpose. Thank you. Thank you very much. OK. All right, so now I'm going to show you a slightly more elaborate example just to illustrate some of the issues that are involved. So here is a rudimentary function that computes the mean for a collection of rational numbers in an array. And so basically, I'm just summing up all of the elements in the array using the plus equals operator from the class. And when I get done, I divide that sum by the number of elements in the collection. And that should give me the arithmetic mean. And were I to replace all those uses of rational with some built-in type, like an integer type or a floating type, the code would be the same. And that's the triumph of operator overloading, is that's what it's supposed to be able to do, is give you those capabilities. And once again, I want to draw your attention to the fact that that return statement, sum divided by divide equals n, that's mixed type arithmetic. You've got a rational on the left and an integer on the right. The compiler silently invokes the converting constructor to make that work. Converting constructors are wonderful for this purpose.
Whereas if you had explicit, it would not do that?
That's right. If you declared the converting constructor explicit, then you would have to explicitly write what is on that last line in the slide. Okay. See, because there are ample examples of classes which have a constructor that can be invoked with one argument where you don't want that implicit conversion. In fact, it's not uncommon to find a container class where you can do something like, say, make me a container of initialized with n, where n is the number of default constructed elements in the container. You don't want that to be an implicit conversion from n into a container type. Things like that. But in this particular case, it works just well, really well. Here's another example, which is that in the return statement there, what I've got, this is computing the median of a presumably ordered collection of rational numbers. Assuming the rationals are already in ascending or descending order, if I want to compute the median value and the number of elements in the collection is even, the way you do that is you compute the arithmetic mean of the two middle elements. So that's what that's doing. It's adding the two middle elements and then dividing by 2. Once again, it's mixed type arithmetic. And so the compiler is going to implicitly convert that 2, that integer, into a rational so that it will use the operator divide that's the non-member function associated with the class. And this is all very much expected behavior. So once again, here it is in more elaborate detail that if you write that, the compiler is actually manufacturing a temporary object initialized with the sum of those two middle elements, and then it's returning the result of that temporary divided by 2. Okay, now here's where it gets interesting, is that rational numbers are a good candidate for turning into a template, because it's easy to imagine that people are going to say, I like what you've done there, but I don't want to be obligated to do all of my arithmetic as long precision. Can't I have long, or something even bigger? Or if I'm pressed for space, maybe I want to represent it with less precision. So we'll turn it into a, and this is when all the conversion rules get really interesting. So turning the rational class into a template is not exceedingly, there's a little bit of tedium involved in throwing template type name in all the right places and tracking down the use of long and replacing it with t, like that. It's not too much, but just got to be careful. And so here is a sketch of the rational class as a template, and once again it's got an assortment of constructors. It has the defaulted copy operations, and then it has the assortment of plus equals minus, the assignment equals, the op equals functions. And then, in order to implement the non-member binary operations, we're going to need a whole set of additional function templates. See, each one of these function templates is implementing plus and divide, etc. Now, this is outside the rational class itself, because we want these operator pluses, operator minus, etc., to be non-member functions. Once again, because we want the conversions to apply on both, either the left or the right operand. And so, but they don't have to be friends, but they're good candidates for inlining as well, maybe even const expering. And so, having transformed our rational class into a class template, things still, hey, it looks like things are humming along. It's behaving in the way we would like it to behave. I can write R1 equals R2 plus R3, and it compiles and it produces credible results. Now let's go back and look at our functions that compute mean. And did they still work? Well, it turns out that this one, it still works great. What we've done is we've turned mean into itself a function template where the type of the elements in the collection is now a parameterized type, so that we could compute the mean of a collection of ints, or the mean of a collection of floats, or the mean of a collection of rational numbers for some precision. And it works. So it looks like everything's great. Until we get to here. This one, it turns out, is a bump in the road. And the bump occurs, once again, on that return expression, which has mixed type arithmetic. What we're doing is we're adding two, in this case, presumably, by the way, if we instantiate this function where type t is a built-in type, this just works great. And all those operators in there turn out to be invocations of the built-in operators. But if we instantiate this type, this function, we invoke it for a type like a collection of rational longs. Turns out the last line doesn't compile now. That the compiler is unable to recognize what's going on. And here's the details of what's going on, is that in the case of this expression, we have two objects of the same type, essentially a sub m minus 1 and a sub added together. That is invoking one of the function templates, the operator plus function template, which takes two rational objects of type t. This is an exact match, and the compiler says, cool. I can figure out that you're invoking that function template operator plus here. But then it sees the divide, and that's a rational of some type t divided by an int. And whereas when we were not using a template, the compiler is able to do that. Now that the type of those elements is the specialization of some rational type, the compiler gets lost. It cannot recognize which divide operator we're referring to. And you can test that out by saying, well, maybe if I force it in the direction that I want it to go, I say not 2, but 2 explicitly converted to type T. Now the compiler says, okay, I can see how to do that. And it does it and produces the expected result. And it has to do with the difference between the overload resolution and template argument deduction, is that the extent to which the compiler is willing to apply conversions to operands in order to find a match. When it comes to overload resolution, where you're not dealing with templatized functions, the compiler does not require that the arguments to an overloaded function be an exact match. It will try a conversion sequence in order to the operands in order to say, if it's not an exact match, can I convert this thing into something that will match? And this is well specified in the standard. There are things known as these built-in conversion sequences and user-defined conversion sequences. And without getting too much into the details, basically, the compiler will try a sequence of up to 3 conversions in order to get from the argument type into the parameter type to make a match. But when the compiler is saying, I've recognized that you're trying to apply a template here, all of a sudden it becomes really stingy about applying conversions to the arguments in order to make a match. And that's what happened here, was that it wasn't willing to automatically apply that converting constructor in order to figure out, if I convert that, now I can do a template specialization of the appropriate operator. And that is, that's an unfortunate consequence. Having the template is really nice because it makes the rational class much more flexible. In fact, there's ample practice of this. For example, the standard library's complex data type is a template which you can specialize for different floating types. Well, for rational, it seems like that's what you want to do too. But the downside is you lose some implicit conversions, which seem like they're the natural thing to do. You lose a little usability. So one way to do it is just take your lumps. Say, okay, it's a good trade-off as far as I'm concerned. I like the flexibility of the rational number class as a template. I'm willing to tolerate that I have to do an explicit conversion now and then. But here's an alternative, is that you could go ahead and say, why don't I, in addition to implementing a divide operator that takes 2 rationals of specialized for type T, overload it with a couple other functions that will be more flexible in their matching. Notice the differences. This is a template with a single type parameter T, which is the precision type of both the left and the right rational number. These 2 templates have 2 type parameters, capital L and capital R. And what they're doing is they are saying, I'm going to give you a way to divide a rational by something that's not a rational, or to divide something that's not a rational by a rational. Now, the presumption is that whatever the type of R is, it's a type that's convertible to the type of rational of L, for example. And that if their conversion doesn't exist, you'll get a failure inside the template instantiation. But on the presumption that that conversion exists, it turns out this works. This will allow you to go ahead and write this original expression back there, the one that's marked at the top of there. You can do it, but it causes an explosion of code. You have to do essentially a trio of function templates for every one of your binary operators. And it's tedious and error prone, not a really preferred solution to this problem. It's not clear it's worth it. So anyway, by the way, I did all this work like 15, 18 years ago. A lot of this was inspired by, I do training for a living, and I use this rational number class in some of my training materials to illustrate a lot of the principles which I was just talking about how these conversions work and how converting constructors play a role in all this. And in my line of work, because I want to cater to my clients, and my different clients will use different, and say, can we use your examples with this compiler? And I want the answer to be yes. You know, I don't want to come in and say you must use, it only works for the GNU compiler toolchain. I haven't tested it with anything else. That usually doesn't go over well commercially. So I was pretty conscientious about testing this stuff. And what I found at the time was I was actually bopping back and forth between 5 different compilers. And 2 of them were perfectly happy with the code that I just showed you, the compiled, linked, and executed. But then I was doing some work and found that 2 of them would accept the compile, but they failed to link. And then there was one other that I'll get to shortly that was giving me interesting feedback, which actually prompted the rest of this lecture. And so here was the version that I was using. In particular, that triggered this analysis was, so I have the rational constructors, as before. I have the member plus equals minus equals. And I had implemented all of the non-member operators, plus, minus, times, and divide, as separate templates. And I hadn't implemented the trio. I just implemented one function, which takes 2 rationals. And I was living with the fact that we had to do the explicit conversion sometimes. But in this version, I also had an operator greater than, which allowed me to compare one rational greater than another rational. And I also had the output operator. And those 2 functions were not implemented as non-member. They were implemented as non-member friends that had direct access to the data members. They weren't implemented the way plus was through the intermediary of plus equals. And I did that, and the compilers were all over the map as to whether or not they were willing to accept this. Some did, some gave link errors. It turned out that one gave me a compile error, which I'll show you in just a moment. So anyway, what really piqued my interest at first was that the ones that were telling me that there were link errors, there it is. There's the friend declaration for operator greater than. And right there in the same header file, right below it, was the template operator greater than that takes 2 rationals of type T. See, that one takes 2 rationals, and this one, this operator greater than, takes 2 rationals. What's your problem, linker? It's right there. Same thing with the output operator, getting the same link errors. Now, just by way of background, before I do any further analysis, I just want to point out that there's a little syntactic quirk in C++, which is that when you're inside the body of a class template like rational T, you can mention either rational or rational angle bracket T, and either of those will work. In other words, this is the same as this. And if you wish, you can toss a coin on every usage and randomly leave out the T's or add them at your wish and upset your colleagues in a code review. But these are equivalent. Okay? So with that little bit of background, here's what I thought was happening before I knew better. Is that when I wrote the friend declaration for the output operator, that since this friend declaration appeared inside the scope of the rational class template, that occurrence of rational right there was as if I had written rational T. In other words, that if I instantiate rational int, I was granting friendship to an output operator that also took a rational int. That's what I thought would happen. And similarly, since Oh, and the other issue was that when I declared the output operator as a non-member function template, since this was not inside the scope of the class rational T, the T there in the argument, in the parameter list, was not an optional T. Okay, and it turns out I had a misunderstanding of what was going on, and let me show you what is really happening. And here's the hint that I got, is that the GNU compiler was the one that would not compile my code. It rejected it with this error message. And it said, friend declaration declares a non-template function. And then, by the way, this is literally what the error said. Okay, I'm not making it up. And then that long parenthetical remark. And I think it's kind of hard to read, so actually what I should say is it didn't give me an error. That was a warning. Yeah, it was a warning. So I've broken it up onto bulleted points to make it a little easier to read that same thing. Let's read it carefully. It says, it was complaining on both the friend declaration for the greater than and the friend declaration for the output operator inside the scope of the class. And it said the friend declaration declares a non-template function. It was saying that both of the, see, conceptually what I was expecting was I have this class template rational T. Every time I instantiate rational int or rational long, I should get a greater than operator that operates on that type. I should get an output operator that operates on that type. And it was telling me, but that thing itself, those greater than operators and those output operators, they weren't templates. They're non-template functions. And it said, if this is not what you intended, then make sure that the function template has already, in other words, if I intended them to be templates and not non-templates, then what I should have done was made sure that they were previously declared as templates. And make sure I use the angle brackets in the function name of the friend declarations, which I didn't do. So by the way, I checked the C++ standard and I actually found, hey, GNU wasn't making this up. It's actually in the language. And this example, I've reformatted a little bit to make it a little easier to read, but this comes right out of the C++ standard. It's still there. And so what we have is, at the bottom, a class template called task. And notice that it has two friend declarations in it. The first of those friend declarations is for something called process, and the second one is called preempt, angle bracketed T. And what it's saying is that the second friend declaration is actually granting friendship to the specialization of a template. And it comes to that conclusion because of the presence of the angle bracketed T in the name, after the name preempt. But if you compare that with the treatment of process, process doesn't have the angle bracketed T. And so what happens is each time you instantiate task with a different argument type, it grants friendship to a function called process, which happens to take a pointer to a task of the right type. But that process function itself is not a template.
It's not defined.
That's right. In other words, I granted friendship to something that wasn't defined anywhere. That's what's happening. Kind of curious. So, what happened was that friend right there, that output operator was not a template. It was granting friendship to a function that wasn't defined. So what this is being more explicit about it. So if you were to instantiate rational with type int, then that class template instantiation would be granting friendship to an output operator that takes a rational int. And again, if you instantiate it with uint64t, it grants friendship to that. But neither of those output operators is a template.
Can you go back to the slide where you showed it was sort of optional whether you had...
Oh, you want to go back?
That's also what made this complicated, right?
You're talking about this, the fact that...
That also made it complicated because you might have randomly chosen one way or the other.
It's a trap. Yeah, it's a syntactic trap that you could fall into if that's what you're suggesting.
I think so.
Yeah. By the way, I didn't mention, but I'll say here that I prefer to do it that way. I leave it out. I think it's less cluttered and it's clearer.
But isn't, when you leave it out, I thought that's a problem too, that you didn't have the angle bracket.
Well, no, it's the special case of the friends, which let's work through these friends. See, so here's what I think that, yes. So this is now where we are from the user's perspective with what I've given you, which is, as a user, I want to be able to use the rational class template and instantiate it for some type like int there. Just create an object R of type rational int, and I want to be able to write it out. The problem is that when I instantiate rational with type int as its type argument, it will grant friendship to a function that's an output operator that takes a rational int, but it never produced a definition for it. And so what happens is I then become responsible to implement that output operator if I want my code to link. And this is what's known as an unfriendly user interface, right? You would not use this class if this was your responsibility to implement those functions. You expect them to be generated somehow by the template. So following the error message or the warning that I got from the GNU compiler, I said, OK, let's try this. It looks like what you want me to do, you being the GNU compiler, is throw those angle bracketed t's in there so that I'm granting friendship to specializations of those functions. In other words, I'm assuming that the greater than operator and the shift operator are themselves function templates, and that somehow or another they will be instantiated upon use. Right? Make sense? Okay, by the way, just as a lexical issue, the spacing there is, you don't need it. So you get these curious looking things like the bow tie operator, or if you turn it sideways, it's a sergeant. There's 3 chevrons for a sergeant. Now here, this was adding to the puzzlement. By the way, I was doing this quite some years ago, and this stuff has since been fixed. But it was interesting to me to see how this chain of quirks among the compilers ultimately led me to a solution that actually still works and holds up well, which is that the GNU compiler accepted. I just put in those angle bracketed t's, and it said, I'm cool with that. It compiled and linked the code. And I stepped back and said, hold it a second. That shouldn't have compiled. Because in order for the compiler to recognize, for example, greater than as a template, you have to declare angle operator greater than as a template first. In other words, this is just using the name, putting angle brackets and a t after it and saying, treat it like it's a template. It was never declared as such. And in fact, the warning that came from G++ said, make sure the function template has already been declared and add the angle brackets after the function name. And despite the warning, the GNU compiler compiled it anyway. So this is what I think they were telling me to do, is if I want the angle bracket on the operator greater than, I have to precede the whole class definition with a declaration of the function template. Right? I have to announce that greater than is a template before I use it as such. Okay? But now look at the part in the teal or green, whatever you want to call that. That is referring to rational angle bracket t before it was declared as a template. What do we do about it? Well, it turns out you need to precede the declaration of the operator greater than by a declaration, not a definition, of the class template. And so when you're all done, you have to have that chain of declarations. And that operator greater than in the middle is a placeholder for every one of the functions that is a function template that you're granting friendship to. Right? And if you want this to work this way, you got to get all these pieces in place. Kind of hard to do. It's kind of tedious. Okay. By the way, so at this point, I went back and I said, okay, let's check this with all of my compilers. And 4 out of 5 ain't bad, but it turned out the 5th one was Visual Studio. And I was not prepared to say, oh, you know, just tell my clients you can't use that tool with my examples. That's just not going to go over well. And Microsoft, their compiler at the time, looked at that angle bracketed T there, and they said, whatever that is, I don't know what that is. Whatever it is, it's a syntax error. It just wouldn't accept that at that spot. And I said, oh, what do I do? And I had a flashback. It took me a little while, but I remembered that, you know, this was, I was doing this work in the late 90s, early part of the millennium, and compilers were still not in agreement about a lot of these corner cases. And so, and I remembered that early versions of the Microsoft compiler had this as a chronic problem, the inability to associate a friend function with a definition that appeared outside the class. And I almost invariably solved the problem by saying, oh, just take the function definition and put it in the class. Now the declaration and the definition are all in the same spot, and it turned out that the compiler wasn't confused anymore. You didn't have to struggle to match up the declaration with the definition. So I refer to this. This is not a widely accepted term, but I think it's a useful term. Is, you know, there are 2 ways that you can have a function have the attribute of being inline, a class member function. One is to explicitly declare it with the keyword inline. The other one is to place its definition inside the class. And people will say, well, that's an inline definition, but how do you distinguish that from one that uses the keyword inline? And I use the Latin phrase in situ, meaning in place or in position. And so this is an in situ definition. Yes?
It's a friend that moved in with you.
Yes. Is that how you like to refer to it, or you just made that one up? A friend with benefits, okay. I'm sorry, run that by me one more time, please.
I think you can put a whole template operator inside your class. As a friend.
How is that different from what I have done here?
You put like a template friend or friend template. I don't remember the syntaxes.
Oh, actually, you use the word template, and you actually make a member template? Yeah.
Can you?
I haven't tried that, so I can't say off the top of my head, but why would, if it's a member template, why would you? Oh, you're talking about putting a member template definition physically inside? I think you can. I think the syntax permits that. Yeah. But in this case, I didn't need it to be a member template. It turns out that just making it a friend function defined inside its class worked. In other words, the effect of this is that, said, this compiled link, but what's going on, let's actually look at this, is that, that when you place not just the declaration, but the definition of a friend function that itself is not a template, but you place it inside a template like that, every time you instantiate the class rational for a different type, it not only grants friendship to a function, but it manufactures the function that it's granting friendship to. That's where this idiom gets its name. That's you're actually, the class template instantiation is making its own friend. And that function, though, itself is not a template. It's a non-template function that is manufactured as a side effect of the template instantiation, which is as good as it being a template. In fact, as you'll see in just a moment, it's actually better than if it were a template.
You called this a corner case, but this is, the stream operator is quite useful.
Well, yeah, I called it it's that this is something that you do often, but it doesn't leverage itself to a lot of other different use cases. It's almost...
Yeah. But it makes you throw your hands up and say, I give up on templates when you can't figure out that wording or that.
Yeah, that's right.
Problem,
Yeah.
Especially linking problems on templates too. Then you start putting
Yeah.
include CPP at the bottom and you don't even know why we're doing.
Yeah, so if you're taking issue with my having called this a corner case, I'll easily relent on that. Okay. Yeah, the judgment of how widely you use this.
I've been burned by this. That's why I'm like, oh yeah,
Yes.
this is a real thing.
This is a real thing.
From that example, take the definition of the operator.
Take the definition of this operator and,
Yeah, you just leave the declaration and definition move out. Will it still work?
you want to just put a declaration for the operator greater than here, but not the definition?
Yeah. So that
The problem is if the definition isn't here, it grants friendship to a function which is not automatically manufactured. The responsibility of manufacturing that definition falls on the user of the rational class, not the author of the class. And that's where the usability issue comes in. But by putting the definition in the class, you not only get the granting of friendship, but you get the manufacturing of the function that you want to grant friendship to.
And if you want to provide a definition, then you need to write this operator outside of the class, and then it should be.
Well, actually, hold that thought. I have some examples that I think will address your concern.
Well, I'm doing this sometimes, but
You're doing it, but yeah, I think people do this, but they don't realize what's happening. It's the backstory that's interesting here. It doesn't compile. That's right. Thank you. Okay. By the way, there's a book by Barton and Nachman, Engineering and Scientific Programming in C++. It was a popular book back in the late 90s. And after I did all this work, and I gave a talk on this many years ago, somebody came up, and I own a copy of Barton and Nachman, and I didn't notice that they were using, I hadn't read the whole book. And if you look through the book, they never mention, there's nothing in the index that points out this technique. They just sort of, in one of their examples, they just threw it in without comment, as if, what else do you do? Without appreciating its significance. So it's not like I invented this originally. I think the first written reference usage of this technique was in that Barton and Nachman book, but it was that I don't think they appreciated that, hey, this is actually a find. They didn't really explain what was going on. It was a throwaway line in the book. So now, by the way, let's revisit this one, which is this problem we had with the compiler's inability to recognize what was going on with this mixed type arithmetic. And that we as a concession, we wound up having to explicitly cast operand, that integer operand 2, into an object of type t. And the reason why I tolerated it was that the cost of fixing it was turning a whole bunch of single templates into a trio of templates and doing that umpteen times for all the different math operators. I said life is too short. But, and so as a reminder here, the fundamental difference between what happened, why it worked when we weren't dealing with templates was when you're dealing with non-template functions, when rational was not a template, it was using it was using overload resolution. And overload resolution uses a fairly generous set of user-defined conversions in an effort to make a match, and it includes the use of converting constructors. But when we switched to turning rational and all of its operators into templates, a lot of those conversions were now not available during template argument deduction to figure out if we could make a match. And so one of the nice properties of this making new friends idiom is that if you turn all of the operators like divide and multiply and add and subtract, instead of making them non-member function templates, you make them friends. You actually move the definition of all of those binary operators into the class and make them friend functions that are defined there. Now you're no longer using template argument deduction. You're back to using overload resolution. And the compiler will use a richer assortment of implicit conversions in order to make the match. In other words, we simply take the rational operator divide, which was a non-member function template, you move it in there. It's no longer a template. It's an overloaded function.
But it's in a template. That's what also.
It's in a template, yeah. But now what happens is you do this even for a function like that, which doesn't need to be a friend. You put it in there. And then what happens is now that divide by 2 compiles without the explicit conversion, which is very nice.
And you didn't have to write all those other.
That's right. I didn't have to write the trio of things. So that raises some questions. You know, it said that, oh, by the way, yeah, that notice that the implementation of the divide operator is it's in terms of divide equals. Divide equals is already a public member function that does the work. There's nothing in the body of that operator divide that mentions num and den directly. It doesn't need to be a friend. So why do we have to throw the keyword friend there? Because if you take the word friend off, now the declaration doesn't compile. Because when you put an operator inside a class like that, the compiler assumes it's a member function. It has a this pointer. And that divide operator becomes a 3-argument divide. And there ain't no such thing. You'll say, well, OK, then get rid of one of those. And so you have it as a member and with 1 argument. But now we're back to the very beginning where we can't have conversions on the left argument. You need it to be a non-member, so you can have conversions on either the left or the right. And it can't be a member. It has to be a non-member. So the question is the friendship necessary? And the answer is, in a sense, no. But if you don't make it a friend, then it becomes a member. Well, but maybe there's a possibility. Why can't we make it static? Because that's the other way to get rid of the this pointer. Make it a static member function. Why can't you do that? Well, because you can't. There's simply a flat-out statement in the standard that says operators cannot be static members of a class. And because it drives overload resolution crazy with creating ambiguities. So that it's just a flat-out rule, you can't do it. And so, in a sense, what we're doing here is we're using friend in a somewhat sneaky fashion. It's a way of turning what would have been a member function into a non-member helper function by getting rid of the this pointer. And so you could argue that conceptually, static might be the better way to declare it, but you can't do it that way. So we're essentially leveraging the behavior of friends. So this is granting friendship when you really don't need to grant friendship. It's really, it's to deny membership. That's what's really happening here. Now, just one little last thing that I want to point out, which I think is interesting, is so the compiler, when you instantiate rational for a type T, it's manufacturing this friend function. Where's it putting it? In what scope does it reside? And friends have a very interesting behavior, which is, oh, by the way, to drive the point home, I've now wrapped the rational class inside this namespace called sax. And if you try to refer to the operator divide outside the class like that, this is a use. I wanted a single line use. I'm trying to take the address of that function, find out if I can point to it. And it turns out that it's in the namespace sax. I just say sax : operator divide. The compiler can't find it. And the reason is it's using ordinary name lookup. And friends that are introduced in a class scope like that are not visible by normal lookup. And so, but it turns out it can be found by something called argument-dependent lookup, which it relies on looking at the argument types to say what class should I go look in, or what namespace should I go look in to find it. But here's an interesting little demo that you can do to demonstrate what's happening, is that if you go ahead and explicitly declare a rational int operator divide like that, so that you actually make the declaration visible by lookup, that access on the bottom line is found. In other words, you've actually introduced a declaration into a scope, and it does exist. And moreover, if you actually turn that into a definition and you use the rational int type, you get a multiply defined symbol. So you can actually find the spot where the compiler put those friends into a particular scope. So they are being manufactured. You can hunt them down, but you normally don't. You just let argument-dependent lookup find them.
Could you have said SACS scope, rational scope operator?
No, because it's not a member of class rational. You can't say SACS : rational : operator, because it's not a member of the rational class.
Even though you could.
Yeah, even though it's there, it's not there. Okay. So anyway, Scott Myers actually has a little bit of advice in his book. He says the rationale for doing this is, it says define non-member functions inside templates when type conversions are desired. I think that's a little bit too vague for my taste. I prefer a wordier but more precise statement, which is when a class template defines a type with an associated binary operator that allows user-defined conversions on its left operand, then you should define, not just declare that operator inside the class template as a non-member friend. That's really the specific use case. Okay, and that's it. There were the references, and thank you very much.